So thank you very much for this invitation to be here and to this very interesting school that has been organized here. It's my fourth time in Bangalore, and it's always a pleasure to meet my colleagues here. So in this set of lectures, I will try to discuss a problem on stochastic thermodynamics, but mainly on the experimental point of view, although I would make a lot of connection with theoretical aspects of the problem. So there are, of course, I cannot do a full picture of that in just 4 hours. But I'll try to do, for those that are not familiar with, to have at least an overview what has been done and what can be done in the future about that. Okay. So first of all, let me thank all the person who work on this subject with me in the past 10 years or more. I mean, 15 years. And all mainly PhD student and postdoc who work in my lab, and then also collaborators, Petrosian Bellon, who are experimentalists, and all this bunch of theoreticians that I have the pleasure of interacting with. Okay, so the idea is the following. So let me make a picture of what stochastic thermodynamics is useful for. Usually we talk about thermodynamics thinking to big machine or for example, to study efficiency. But indeed, today, with nanotechnology or biology, etc., we are dealing with the very, very small energy, tiny energy. So for example, and for example, you can think to, we will see, very, very small motors. And so indeed, this is a picture of the typical dissipation that, in log scale, is a function of the size of the characteristics type of your system, okay? And now you see that if you are in the scales of meters, you see that we think to steam engine, car engine. But if you go to very small mesoscopic scales, around 1 micron to the order of nanometers, you see that the typical amount of energy goes down. And this is typically KBT, 1 KBT over seconds in terms of power. That is the energy, the typical energy of your heat bath that is in contact with your small system. And then you realize immediately that the motor or the nanotechnology, the nanotechnological effect, so the biological motors, are in a situation where the fluctuations of the system or the thermal bath can be important. And so the question that I want to discuss, do fluctuation play a role in thermodynamic laws? And if, what kind of role do they play? Okay, this is the answer, the 2 questions that I want to analyze in this series of lectures, okay? So the typical object that I have in mind is for example, a Brownian particle driven in a non-equilibrium steady state, okay, like this. This is just a trapped particle by a laser beam that is turning around and is pushing the particle over there. Then typically, for example, you can look at microactuator, for example, a small cantilever that are used, for example, typically to measure Casimir forces, the interaction, for example, of a sphere with the plane and other things, or as simply as a microactuators. These are objects, again, very, very small, where again thermal fluctuation play a role. Or, for example, you can think to fluctuation given in heat transfers, in which you couple, for example, 2 heat baths just because of their fluctuations, and you want to measure the heat flux that is happening between the two heat baths. Okay, so here there are other applications that certainly I will discuss. The question of the Maxwell demon, that actually it's very important in this context, because you will see that what was in the past just thought as Gedanken experiments now can be realized, and we can understand a lot of things about connections of informations at thermodynamics. Okay, so these are other typical examples, for example, that you want to think about. For example, you want to study the flexibility of a nanotube, or you can measure, for example, the heat current on a nanowire. Or for example, here is a torsion pendulum of the scale of that. This is typical micromotors. Or for example, you want to measure the free energy of a single DNA hairpin. Okay, so these are typical examples, and I will show you how this can be done typically. Okay, so okay, but what is important to say is that fluctuations are important not only in microsystem. Indeed, many of these kind of problem of stochastic thermodynamics can be also useful in microscopic system, typically, for example, in a turbulent flow, for example, here you see, or for example, in a granular gas that is shaken by a piston. It doesn't work? Okay. You see, this is just a granular gas that is shaken. And so you want to know, this is a clear an out of equilibrium system that is driven again in an equilibrium steady state. And then you want to know again what if law of thermodynamics can be applied in such a system where for example, the collisions are dissipative instead than in molecular case that are not. Okay. So this would be the typical there is a question. Yes. There's this one. Oh, sorry, I didn't say. This is a typical column of fluids that is eaten from below and cooled from above. So it's just thermal convection. And what we are seeing is just the hot plumes that are moving inside the fluid. Okay, thank you for the question. Actually, I did not explain. Okay. So there are a lot of things that I can discuss. But first of all, I want to recall the 3 or 4 basic notions of thermodynamics in order to establish a common language for everybody. And then I want to show what we know about equilibrium statistical physics. That is how, for example, equilibrium statistical physics can be used in order, for example, to calibrate instrumentation when you're in a lab. Okay. And then, so these typical cases, for example, again, are optical tweezers, active and passive microrheology, electrical circuits, analogy and difference with the mechanical system, and then for harmonic oscillators. Then we will go to out of equilibrium. When I drive this system, for example, I apply the external forces and I want to measure, for example, the amount of work that I'm doing on these micro devices in order to perform some task. Okay, so the question that I will, the main subject that I will recall for some of you, or eventually this is something that is new for others, is the fluctuation theorems, the Janskinski and Crookes inequality, and the stochastic entropy. And then I will show you this in terms of experimental approach. For example, in harmonic oscillator, in the case of stochastic resonance and fluctuation-driven heat fluxes. And then I will show how this system can be actually used in order to do practical measurements that are quite useful, for example, especially, for example, in biophysics. Then there are the other problem that I will not discuss all of them, but certainly I will skip this, I mean, which is related to the last two pictures, in the sense that I have no time to discuss the application of this on granular media, for example, or other things. Instead, I will spend some time in something on which we work a lot in the last 10 years, is the connection between information and thermodynamics, and the problem of the Maxwell demon that, as I said, that nowadays becomes a very, very useful system in order to perform. And then I don't know whether I will have time, but okay, we will see. There is the question of the fluctuation dissipation theorem in equilibrium steady state. We know that fluctuation dissipation theorem relates the response of the system to an external force in the case of the linear perturbation, and to the natural fluctuations of the system, okay? But now, if the system is driven out of equilibrium, the standard formulation of fluctuation dissipation theorem doesn't hold, and there are interesting variations of that, okay? And then, okay, the last point, we will see whether we discuss this or this, is the engineered weak equilibration. And then, okay, there are questions on how, for example, you can reach equilibrium much faster than the natural relaxation time of the system, okay? So let me start. I apologize, I start from far away, but I mean, I said I want to establish a common language. So you remember that the first principle, okay, tells us about the fact that, okay, the internal energy of the system, when you make the difference of internal energy between a state A and B, is equal to the work performed on the system to go to A and B minus the amount of heat that has been dissipated towards the heat bath, okay? Then the second, this is an important statement about the second law. We will go back on this to definition of the second law in the context of the Maxwell demon. Because this, especially what we will be interested in, is the fact that the formulation is based on the Lord Kelvin statement of the second law. It is that no process is possible in which the sole result is the absorption of heat from reservoir and this complete conversion into work, okay? This is actually the key points of the Maxwell demon, and we will discuss this a lot in one of the lectures, okay? And then, okay, there is the important point about the entropy that thermodynamics is defined, as we know, as the ratio of the heat with respect to the temperature. And we have a statistical definition of that is just the sum of the probability of a certain state with respect to the log of the probability. This is the definition. Okay, there is a white space that, okay, the question is whether this entropy is related or not to the information entropy, that is the Shannon entropy, okay? So then there is the question, as I said, of the fluctuations. This is a typical, I change the scale anyway. So this is a typical picture that you see in the microscope. For example, these are colloidal particles of about 1 micron, 2 microns of diameters that are moving inside the water. And okay, you see that they are shaken by the collisions with the water that is surrounding them. And okay, this is 10 times faster what is going on. And then, for example, you record the typical trajectories, and then you see that already averaging the standard deviation of the position of this trajectory, you see that indeed you just a few, you see that the variance increases as a function of time that is almost linear. Okay, you need to average on many trajectories in order to get the linear behavior and thus obtaining the Einstein relation, which relates the variance to the diffusion coefficient KBT over the viscous dissipation. Okay. This is just a picture, and okay, there is another point that that is interesting, that is probably not is less known for people, for example, working in soft matter, but for example, is the fact that Nyquist, well before the appearance of the fluctuation dissipation theorem, find with the thermodynamic argument of two interacting conductors that there is in any electrical conductor, there is a noise that whose spectral density is given by 4 kBT. R is the resistance, the ohmic resistance of the conductor times the temperature in which the conductor is connected. So this is was almost just a few years ago, a few years after the Einstein relation on Brownian motions. Okay, and then you see that again this interesting relationship, because if you compare this relation with this, you see that again here there is the variance that is related to the dissipation of the system, the diffusivity constant, and here you see that again the fluctuations of the system. This is just the amplitude of the spectral density of the fluctuation of the electrical fluctuation across the conductor, and then you see that again is proportional to the dissipation. Okay. So to the dissipative part. Okay, now the point is that we have seen that, for example, there were free particles moving inside the water, but now you can confine them, okay? And you, for example, if you are looking at fluctuations of the fluid, what you do, you take an optical tweezer, we will see, in which you can show that indeed you have produce an harmonic potential in the focal points of the strongly converging laser beam. Okay, and then the similar things that you have here. So sorry, this is we will go back on this point, but you see there is a stiffness that is actually given by the intensity of the laser beam. Okay, and the geometry, of course. And the X is just the position in this case. It's clear that this is true in all positions. For example, Y, that is the direction perpendicular to the board, and zeta, that is the direction of propagation of the laser. Okay, so you have the particle is trapped inside there. Okay, we will see more. And for example, the same thing can be done in with the electrical fluctuations if you put a capacitance that actually reduce the spectrum of the fluctuations because of the typical cutoff of the system, cutoff time of the system is given by the product of R times C. Okay, so optical tweezers. I don't want to spend much time over ideas. This is not the place to explain. But I want to remember that just asking got the Nobel Prize in 2018 for this for having invented this technique that actually today is very useful in many fields, going from rheology to, for example, biological to biophysics, etc. Okay, I don't go into the details of that. Okay, I put only these slides if you have questions anyway, so in order to be precise in the answers, but actually I don't need. What I need is just to show a typical experiment when you have a laser beam, for example, that is strongly focused on inside the cell that contains colloids, for example, that immersed into water. And so, as I said, the important thing that you keep in mind that you produce on a first approximations an harmonic potential that is actually trapping the colloid. Okay. You can ask questions, you can stop me, but there are no problems, okay? So then, for example, you have camera in order to detect the position of the particle, or eventually you can do position-sensitive detectors that allows you to measure the X. And okay, so the question is now, okay, this is typically what you get. Yes. Yes. Yes.
Okay. So there is one diode laser, another helium neon laser.
There is this is a linear neon laser that is, but I mean you can do with the infrared or whatever. I mean this is strongly focused by an objective inside the cell. Okay. Then there are colloids that can be inside the solvent. That in the picture that I'm showing is just water. Okay. And this is a transparent bead, okay? And so if you want, the trapping effect is given by the difference of the index of refractions of the colloids with respect to the solvent, okay?
My question was, what is the purpose of having two different lasers?
Okay, the laser on the side. Okay, I'll tell you. Okay. Because part of the drawing is kept. Good point. I mean, okay, the point is the following: that one laser is used for the trapping, okay, and the other it is very much more very small power of the one that is trapping, used for detecting very fast deposition of the particle. So the particle actually the laser goes through the particle, which is actually acting as a lens. And so when the particle moves, it's deflecting both laser, but what we are interested in the small power laser, okay, that is just refocused correctly in order. And then here on the top that is missed, okay, there is a position sensitive detector, which actually measure the position of the beam, okay, as a function of time. And this allows you to measure the position very precisely, the position of the particle. Does it answer to you? Yes. For example, okay, as we have, look, there is, yes, no, probably no, is the, I have a drawing that explains this quite well. Well, I don't, I know I suppressed. Sorry, but anyway, I can do the drawing the point is that in order to be to have the maximum sensitivity, you know, suppose that is the colloid that is trapped by the laser. What you want that the trapping laser is like this, okay, and then the particle is attracted on the point of maximum intensity, okay. And the other laser, okay, what you do, you plan to focus it before, okay, roughly on the focal point position of the particle, okay, in such a way that here the particle, the laser goes out almost parallel, okay, and so you see that if the particle move, okay, this beam is deflected, okay. And so if I have a position sensitive detector, I can measure the deflection. So the idea, many of the things can be done for fast camera, okay, till 1,000, 1,500 hertz, okay. But if you want to measure really very, very fast fluctuations, for example, to study microrheology at very, very fast, very high frequency, the camera, I mean, cannot follow, and so you measure the position with the position sensitive detector. Okay. is also it's a matter of time, because at the end of the story with camera you can have a very good resolution about 1 nanometer, because what you do with the camera, of course, you take the picture of your colloids, and then you measure the center of mass of your intensity. Okay, and so as you have many pixels, your resolution is reduced by the 1 over the square root of the number of pixels that you have. And so starting even for, sorry, no, it's 1 over n, the number of pixels that you have, okay? So at this point, you see that you can reach a resolution between 1 and 5 nanometers, okay, even with the camera. Okay, then of course, with that, I mean, the position sensitive detector, certainly you have a better resolution. Okay. Yeah, no, but I mean, we are here for discussing. I mean, it's a pleasure to answer.
So the focusing laser,
yeah,
one which is actually the tripping,
yeah,
must be of higher magnitude and intensity.
Yeah.
Compared to the one who is
used for detection.
Used for you know, locating.
Yeah, yeah, exactly. For detections of the position. Yeah. It's much smaller. I mean, here we are talking about 10, 20 milliwatts, and the other is much less than 1 milliwatt. Okay. Yeah. Okay. Yes, I thought this is for the camera. Okay, and then okay, with the optical filters we can suppress the light that we don't want. Yeah. Okay. Other questions? Okay. Good. I like that you do experimental questions. It's not often that appears. So this is typically what is happening. You see, this is just if you have 4 beams. And then you can trap 4 particles, and then you can study interaction between the particles. And then there is something that I will use a lot in the rest. I mean, you can construct more complex potential by doing, for example, putting 2 lasers. And then you see that now the particle is actually jumping between the 2 lasers. Why? Because the particle is attracted both by this point of maximum intensity and this one. Okay, though sometimes it's trapped over there, but then thermal fluctuations allows the particle to jump on the other. Yes. Okay, yes, okay, good. Yeah, usually you can do with 2 beams, okay, but the easiest way of doing is to use an acousto-optical deflectors, okay, in order that you can switch so fast that actually the particle doesn't know that there are 2 beams, okay. And so it's just seen as a static beam. Okay. Anyway, there are some details that if you do very sophisticated measurements, actually you realize that the kick that the particle received is not totally innocent in some cases. Okay. But I mean, in standard experiment, it doesn't matter. You can just switch the 2 lasers very fast in order to have almost 2 constant lasers in the 2 positions. Okay. So this is okay. Those typically what is happening. So all of this, when a particle is trapped like this, can be described by a Langevin equation of the first order. You see that I completely neglect in this case the inertial part, so there is no mass. Indeed, the frequency in which the inertia appears for this small particle is very, very high. So for usual application, doesn't matter. And all the phenomenon can be described quite well by first order Langevin equations, where gamma is just the sorry, it's just the viscous dissipation, and then okay, this is just the stiffness. I put T because for example, making the laser intensity time dependent, you can, of course, modulate this stiffness by changing the intensity. Okay, and then there is this noise term, okay, that is given by the diffusion coefficient, that is given by gamma T over gamma, where gamma is the equivalent viscosity of the system. And then, okay, Xi is just a delta correlated noise that is added to the equations. What it happened that the fluctuation, the probability distribution of fluctuation is Gaussian with a standard deviation that is given by KBT over the stiffness, okay? We will see where this is coming from. Okay, this is coming from, of course, this is standard, yeah. K, it might be a function of keys because K, as I said, and you have to keep in mind that K is proportional to the trapping intensity. Okay, so if I modulate the trapping intensity, K can be a function of T. Okay, so in some cases, or it can be a constant. Oh, no, usually it's a constant. But then, if you want to do specific experiment, so for example, if you want to change suddenly the stiffness of the system and then to modulate the stiffness, then you can modulate the intensity of the laser beam, so K becomes time dependent, okay, in general. So typically with K, when K is constant, you have that you measure the fluctuation. You see this is perfect Gaussian, and by fitting the Gaussian, once you have calibrated your space measurement, you see you can extract the stiffness of the system. So this is typically what the first thing that I want to say. This is equilibrium thermodynamics. Actually, in this case, allows us to calibrate the system and to know how big is the stiffness of the laser. Okay. Then, for example, what you can do power spectral density of the system. You see they do the power spectrum of the fluctuations. And okay, this is meter square over Hertz, this of the position. And then it is a function of the frequency. You see this is around 1000 Hertz. And this is what is called the cutoff frequency that is given by the ratio of the viscosity times over the stiffness. And then you see that the spectrum can be perfectly fitted by a Lorentzian that, of course, it must be like so if you look the fact that this equation is that the motion is described by this equation. So the spectrum must be like this. Is it clear that for everybody that if I use this equation, the spectrum should be that? As is a school, I mean, I don't mind. Okay, good. Yes.
Can you go back to the previous
Yes.
slide? So, no,
still one?
Longevity, yeah. So why is that gamma there in that stochastic force in the right hand side, square root of T?
Okay. Why this one?
Yep.
Because usually inside here you should have two. Okay, this is a kind of normalization, but you have 2 kBT gamma. Okay. Okay. And so that's because we like to use sometimes the diffusion coefficient as Einstein does. But anyway, otherwise you can write in terms of gamma. Sometimes the 2 is put inside there instead of okay. So there are different ways of writing. Okay. Other questions? Yes. Yes. Next. Yeah.
10 to the power minus 21 is your floor. What do you do to get such a low floor? I mean, mechanical noises?
Well, this the noise floor it's a little less, okay. But this is usually in the case of the camera is actually the resolutions, and in the case of precision sensitive detector is the electronics. Yeah. Yeah. Okay, because all the experiment is mounted on the floating table, okay, and then everything, the montage is very solid. That's it, and then the only things that that remains is just this floor noise that is given. I mean, in the two cases by the camera by the resolution, and in the case of the position sensitivity detector by the electronic noise. Okay. Yeah. Yeah. Ah, okay. No, because okay. This is rather technical question, but anyway, can be of interest of everybody. The point is that I didn't put, but I have the picture where I put this. We will see in the case of the AFM technique, okay, with the cantilever. The actual noise, you say, for example, suppose that this is what Arne is doing with position sensitive detector, okay? So here you see, you start from here, but then if I suppress completely the by electric noise like this, okay, and then the 1/f is like this, okay. So the fluctuation are very large with respect to the 1/f noise. That is the reason why you don't see, okay. And then, okay, to be even more technical, the point is the following, that, for example, in IFM is much more hard to have such situations, because everything is very solid with respect to the external mounting, okay? Whereas in the case of the particle, you see that indeed, the particle is trapped, okay? So suppose that the cell is moving a little, okay? You see the transfer of the vibration of the cell to the particle is much less than in the case in which I have a solid stuff, for example, as a cantilever, in which in this case the vibration of all the mount will be transferred to the cantilever. Okay. So, other questions?
So,
yeah.
In the case that you have a time-dependent spring constant,
Yes.
how do you modulate? How do you calibrate the trap?
No. This is easy because suppose that I do that for one intensity, okay? Then I know that okay, this is this value. And then I can do other 2-3 points at different intensity constant. But usually, if you have not done bad things, is linear in the intensity, the stiffness. So you know that if you modulate the amount of change of the intensity actually corresponds to the amount of change of K. Okay. Yes.
So in the numerator of this power spectrum,
Yeah.
there is this gamma, which is the dissipation and also the temperature. So
yes.
Usually we think that if we increase the temperature, then I mean the dissipation and temperature we think are not in the same term. So here, if we increase temperature or if we increase viscosity, the power spectrum.
Ah, yes.
So
no. Okay. Understand? You mean that indeed, if I translate your question, is that the viscous coefficients depend also on temperature. This is your point. No, but what is the point? I don't understand.
Yeah, so I meant that the movement of the particle decreases with increasing dissipation, the viscosity, but with temperature it increases. So
no, okay.
Goes
Okay.
up
No. Okay. Wait. You have to look at the amount of energy. Okay, if I understand correctly, you mean that if the particle move dissipates with respect to the heat buff. First of all, the heat buff has a thermal inertia that millions of times larger than of the particle. So the increase of temperature of the heat buff, I mean, is not a matter. Okay. So even the particle dissipates, okay? I mean, it's so small, okay? And then you have to, in this case, you see that this is in Kelvin, okay? So this is 300 with respect to variation of temperature that could be millikelvin, okay? Something like that. So this is not a matter. Instead, I mean, what you are right, it might be that the laser beam, okay, is partially absorbed by the particle depending on the kind of particle that you are using. Or for example, if the liquid is partially absorbing the wavelength of the laser, okay, in such a case, you are heating the system, okay? And so that is not negligible. Actually, you can detect the increase of temperature, okay, just by measuring the viscosity, okay? You do this fit, okay, on that, and then by measuring how gamma evolves as a function of the intensity of the laser, you can know how much the temperature on the particle is. But still, with even a very high power, you have a maximum, a few degrees of increasing on the particles. So still, with respect to the 300 Kelvin, remains negligible, okay, within a few percent.
Thank you.
Okay. Other question? Okay. So this is okay. This is just to remember the definition of the fluctuation dissipation theorem. As I said, this is written in terms of frequency. Okay. I'm using F here because this is actually a power spectral density in terms of F, not of omega. And when it's written like this, and so you know that this power spectral density is related to the imaginary part of the response of the system as a function of omega, and so it takes this form. And actually, it can be easily computed. You see that because of the equation that we have. This is actually you expect to find such a kind of spectrum, okay? And so this is another thing that is very useful actually to measure, to make measurements using standard rules of equilibrium thermodynamics. Because why? Suppose that usually, well, this is a soft matter school, so probably you are familiar with that. For example, you want to characterize the rheology of the system. What you usually do, for example, you take a layer, you apply a shear, and then you measure, for example, the phasing between the applied force and the response of the system, and then you know the shear that is known. But for example, here, what I could do, I can, for example, move the particle. I will show you in the next slides, and then to measure the response of the system. But now, suppose that you cannot do that, and there are many fluids in which you don't want to do this, and you want to look just at fluctuations, okay? And now you see that indeed, you can use many tools of equilibrium statistical physics in order to get the right answer. Suppose that now I take this spectrum, okay? This is an easy case, okay? And so I measure this. I know the fluctuation dissipation theorem, which give me the imaginary part of the response. So, but how do I get the real part? And then, I mean, you can play a game, use the Kramer-Screaming relations that relates, okay, the response, the imaginary and the real part of the response. These are typical, okay, no, this is just correlation function written in the other way, okay, I can skip. But then you see that the imaginary part, the real part of the system is related to the real part is related to the imaginary part via the Kramer-Screening relations that can be written in terms of power spectral density like this. So, okay, then there are techniques that I will not describe in order to improve the integration of this integral passing from Fourier transform. But in principle, you see that again, equilibrium statistical physics is helping us in doing measurements in many cases. Okay, and this is of course no, I don't go into that. I will show how you get the real part. But there are ways to check that you have done, for example, in this case, is possible. What you do, you can measure directly the response. And how you do this, for example, you apply, for example, in your Langevin equation, what you do now, instead of modulating the intensity of the laser beam, you modulate the positions, okay? So you measure a shift. So this is equivalent to apply an external force to the system. So you see they can measure the response of the system at a different frequency. And so I can have a characterization of the response. And then in this case, I can compare the response measure with what is called active rheology, in which active because you apply an external force, to passive rheology, in which you're just measuring thermal fluctuations. So you have two methods that allows you to precisely characterize the rheology of the system. This is a simple case because you have just one viscosity, but suppose that you have no Maxwellian fluids, no Newton fluids, and you see that when you have this scholastic case, this can be useful. Okay. Again, for example, let me take the case in which a particle is jumping between the two lasers. And again, we want to construct now the shape of your potential that you have constructed in this way. So what you do, you measure again the probability distribution of the particle by measuring the position. Then you know that as you are in equilibrium, the probability distribution of the position has to be given by U of X, the trapping potential over KBT, okay? So you inverse these relations, okay? And that's what you get in this case, okay? You see this is a typical quartic potential with two wells, okay? And then, okay, you can fit all the parameters, and then you can check, for example, that, okay, sorry, it moved. Anyway, so this is the barrier, actually, the barrier is about 2 kBt, okay? And then, for example, you can check the Kramers rate, the jumping time between the two wells, okay? So this allows you, again, to characterize your system and to have a precise knowledge of what you're doing, okay? Okay, the other possibility, this is an alternative possibility that is very precise, actually, in this case, to use the tail balance instead of using just the value distribution of the potential. And the reason of that is that well, this is a matter of statistics, but anyway, you can use, for example, the tail balance. It is the transition probability to go from the position I to the position J, divided the reverse process. Okay, and this is does delta uj, and then you integrate this, and you get the potential. Okay, so you have two methods in order to verify that you have done correct. Yes. At least it depends. Okay, but usually, to have, I mean, the standard viscosity, you have to be above 20 microns, because below 20 microns, you have corrections. And corrections are given by the fact that is not anymore just the Stokes law that is determined the viscosity, but is the fact that you have a shear of the particle on the surface. Yeah. No, okay, no, okay. First of all, yes, well, we can discuss a lot about that. Anyway, usually what you do, okay, suppose that here entrapping, this is 20 microns, okay? Usually the the other glass windows confining is much far. If this is 20 microns, this is at least 50. Okay. Okay. So yeah, there are at least. So you know that at this point the beam is diverging, so it doesn't match. And then okay, you have to take into account that the first interface is the first interface is water glass. So the amount of intensity which comes back, it's absolutely negligible with respect to the amount of energy that you are sending. Okay. Yes. Away from the bottom surface. Yeah. It depends on the size. Yes. Because, yeah, sure. Because if I call this, let's say, small h, okay, there are corrections that actually depend on R over H. Okay. Yes. I don't remember the question, but the first term should be 1 over 16 R over H, something like that. Other questions? Okay, good. So we are here. I'll skip this. It can be all of this can be done, for example, in electric circuits. I'll skip all that because okay, it's just the same. For example, in the case of the torsion pendulum, for example, you need to calibrate also the inertia. Okay. This is a typical example that we will use. For example, you have a mirror that in this case, okay, is suspended by wires, okay, and the mirror, of course, can rotate in these directions, okay, like this, making an angle theta with respect to the position. Then you have two laser beam that doing interference in a very sophisticated interferometer apparatus that allows you to measure very precisely the theta. Okay, so typical displacement in this case for this system are 3 nanoradians, the standard deviation of the fluctuation induced by the noise. Okay, now you see that the noise again is given by kBt over c, and this is of course given by equipartitions that tells you that each degrees of freedom has to contribute as a kBt to the total energy. Okay, so here you see that the noise of the system is very, very small with respect to that is 25 picoradians. So the signal to noise ratio in this system is around 100. Okay, so okay, this is just descriptions. Okay, so in this case, things are slightly more complicated because you have also the inertial term that is to be into account. Then sometimes, very often, you have viscoelastic fluids that has to be described by the fact that you have a memory effect in your viscosity, and then okay, there is the standard elastic component that is given by the stiffness of your wire. Okay, and then okay, as you have a rotation, there is a torque that is applied, and this is again the eta. Now you see that I can put this in the Fourier transform, and I can use again fluctuation dissipation theorem, and getting in this way the power spectrum of the system. Notice that because of this, I am forced to introduce an imaginary component of the elasticity that is just given by the presence of this term. That is, I cannot write the viscosity only as omega of nu, but in principle, I have also an imaginary part that is coming by the effect of the viscous of this delay. So this is what you get. I mean, so this answer to your questions about the noise. This is another system, but you see that even in this case, the instrumental noise is very, very small. This is in meter over square root of hertz. Okay, so the noise is around 10 minus 10 minus 14 meters. Okay, this is when the system is in air. You see that the resonance is quite well, and then when it's inside the fluid, okay? And now what is interesting here, that indeed the much part of the viscoelastic part is coming by the viscoelasticity of the metals that are doing the wire, okay? And then, okay, you can show this, and actually you can test, I mean, if you have done the good fit of your system by doing, for example, by measuring the spectrum using the response. These are the small points, okay, in which you have measured the response of the system directly. And this is the noise spectrum. And you see that indeed the calibration was very good because we satisfied completely fluctuation dissipation theorem as we are in equilibrium. Okay? Questions? Yes. What? Yes, meter of square root of Hertz. Yeah.
Sorry.
Yes, it's meter over square root of Hertz.
So in torsional sense, are we not measuring radians or something? Like, why is it meter? That's what I didn't understand.
Yes, okay. Yes, sure. But thank you for your questions. Okay. Indeed, this is the resolution of what you're getting exactly on the interferometers. Okay. But then if you want to measure the theta, that is easy because you know the distance of the two beams. Okay. So by knowing the difference between them, you know the torsion angle of that. You can calibrate very precisely. Okay. Two? Yes, yes, yes. No. Because the inertia is related to kinetic energy. Then in this case, in the case of inertial system, you have 2 degrees of freedom that are independent. One is the velocity, and one is the position. Okay. So in one case, you have actually 2 variants that you can use because you have v squared that must be kBt. Okay, suppose that I am in a system over m, okay? If I, for example, just translating system, okay, and then I have E squared that over K, okay? Or in this case, or in the other case, I have theta dot square that is will be the kBt over inertia, and this will be, for example, theta square that will be over kBt over C, the one that I call, okay? Because what I am using just equipartition, okay? So for theta dot square, theta dot, but not theta, you said theta. So theta dot, right, if I is small, theta dot will be large, sure, okay? Yeah. The one, this the power, this one, the one over F. Yeah, this is just, I mean, it just the metals that in any case has viscous dissipation inside. Okay, and this is just gives you a sort of imaginary part of the Young modulus. Okay, and this is the reason why. Things which actually work hard, like so they start moving that material's elasticity is like things like copper. Yeah, somehow yes, yeah. But the main message is this: is that the metal is dissipating inside. Okay. And I can show many measurements. For example, as we are discussing about all these kind of things, you suppose that now I'm taking a an IFM cantilever, okay? So that is oscillating like this, very small, and then I do this just with the monocrystals of silicon, okay? And then you see that this effect completely disappears. But now I take the same one and I put just a layer of gold, okay? And then you see that there's a 1/f noise that appears. That is just due to the fact that, as you know, the gold is very plastic, and so you have a lot of dissipation inside, okay? And so then you can describe this as an imaginary part of the Young modulus, okay? Other questions? Okay, so this is, yes, okay, so let me summarize what I wanted to say about equilibrium statistical physics and experiment. What I hope that I give you the main messages is the fact that there are laws of standard equilibrium thermodynamics that are commonly used in lab in order to calibrate experiments. Okay, what we have used is just equipartition, as I said, the Gibbs statistics in order to reconstruct the potential, or the detail balance in order again to construct the potential. Then fluctuation dissipation theorem that allows us to relate the imaginary part of the response to the spectrum of the fluctuations. And all this allows us to calibrate optical traps, electrical circuits, and harmonic oscillators. And the last point that I pointed out was that using fluctuation dissipation theorem and Kramer-Skreining relations, one can extract the response of the system using only the thermal fluctuations without doing any kind of perturbations, okay? This was the main messages about equilibrium thermodynamics.
One question, you know, the where you had that slow decay of the, you know, viscoelasticity at low frequencies. Yeah. So how do you, can you use that, and how do you use that to calculate the viscoelastic response function?
Okay, this is okay. So it's technical, but it's like this, because if you assume the simplest, as the range of frequency in which harmonics is small, you may assume that the Young modulus, etc., in this region are constant. Okay, so you can do as you do, for example, when you do the electric response, in which you have absorption, for example, you put an imaginary part. Here, as you have a dissipative part of the elastic coefficient, you put an imaginary coefficient. Okay, and then you see that this is easy. You inject this into that, and then you find that this is the right spectrum that you expect. And now you see that why you have such a 1/f noise. This is just coming from the fluctuation theorem, because you see that at a very low frequency, these guys go 0, okay? And what remains is just C1, 2 over omega, okay? And this is what remains because all the other terms with small frequency are constant, okay? And so you can extract very precisely C1, 2 that turns out to be 10 minus 3 roughly 10 minus C. That is what you usually find in metals. Okay, so that is a good measure.
The range of omega is very small.
Yeah. The range of omega. I mean, you see that. Then the real fluctuations of the system comes out. I mean, so the real dissipation. You see that after the frequency about 10 Hertz, you see that the system is flattening. That is the right response for a viscous dissipation. Okay, yeah. But you see that if I do inner, you see that is as the viscosity of the air is very small. You see that is interesting because this power law is continuing. Okay. Okay. Good. Okay, so okay. Now let us go to out of equilibrium. Now, okay. So what I wanted to do now is the following. Suppose that I want to do the simplest out of equilibrium system that can be realized. And what it is just a thermal conductor connected to two thermal baths at different temperatures, okay? And then the second principle tells us that in average, the heat flux goes from the hot to the cold reservoir, okay? But the second principle doesn't tell anything about fluctuations, okay? There is no statement on the second principle of fluctuations, okay? And I can imagine that in a small system where fluctuations plays an important role, I might have rare events in which the heat flow goes in the wrong directions, okay? And so it's interesting to ask, I mean, what is the probability that the heat flows from the cold to the hot reservoir? Okay, of course, in average, the mean has to be in the good directions, but in principle, I might have events in which the system, the heat goes in the wrong one, okay? And notice that the typical cases can appear, for example, in very minor system when I'm measuring the heat flux, for example, along a nanowire, as I shown you before. And what is interesting in this experiment, they cannot measure the fluctuations because it's already very difficult to measure the mean values. But in any case, this is typical case in which this kind of things can happen. Okay, and now instead, I mean, there is a much simpler case where this can be observed. Remember what I said about the Nyquist noise of a conductor. Now suppose that what I'm doing, and do a more simple experiment of that, I take a resistance, okay, and then I measure the current that is flowing from A to B, okay? And now you see, if you measure this current, which is very, for example, a certain conductor can be very, of course, has to be very small for doing this measurement. But you see, if this current is very small, you see, this is 0.3 picometers, so 3 minus 13 ampere. Okay, you see, this is the mean value, okay? But now you see that there are fluctuations, and you see that indeed, okay, you see there are many events in this case in which the current is flowing let's say in the wrong direction, that is in the direction that is opposite to the mean, okay? And so I would like to know, for example, the probability of these events, okay? Notice that in this case, the injected power, okay, that is the Joule dissipation of the system is extremely small, 10 minus 19, okay? But now I wanted to show you another case, okay, in dynamical systems, okay? Now where the fluctuation now are intrinsic to the system. And the example that I like to give is the following. Suppose that I take a pendulum, okay, and I put it in a turbulent flow, okay? And now you see that, of course, in average, the displacement will be on the direction of imposed by the wind that is blowing. But if the wind is very turbulent, okay, it might happen that the pendulum, okay, because of fluctuation, moves on the other directions, okay? And then again, I would like to know, okay, this is actually typically what you can measure in a wind tunnel. You see that if I measure the force on the pendulum, you see that again, in average, the force is positive, but sometimes it becomes negative, okay? And so again, you see here the difference is very small. This is the injected power is 0.1 watt with respect to 10 minus 19 watt that I had before, okay? So you see that the situation is very different. In this case, the fluctuation is given by the thermal, but in any case, there is these questions, for example, why you have a behavior that go in the other directions of the mean. Actually, is as a sign that is different from the mean. Okay, and so in the next part of this talk, why it doesn't? Ah, okay. No, what is happening? Okay. No, there is something that is missed. I don't know why. Okay. Anyway, what I want to understand is this probability. Okay. I will forget for the moment this kind of problem in the dynamical system. It can be discussed, but probably I have no time of doing. So I will stick about the thermal fluctuations. Okay. And so to do index, I go back to my preferred example, that is the torsion pendulum. Okay. So we have characterized the equilibrium situations. We have calibrated the system. We perfectly know all the coefficients. Okay. And so what do I want to do? Wow. Okay. So, okay. Now what I want to do, I want to apply the torque. Okay. And in order to do this torque, what I do, I put a wire behind the system. I put the system inside a magnetic field. Okay, then I go, I let a current to go into the wire, and so I have a torque that is applied to my torsion pendulum. Okay, so I neglect for the moment the viscous part because it's very low frequency, so it doesn't change too much the philosophy of what I'm saying. Also, the amount of energy of that is small. So I'll stick on these equations where now there is you see the system is driven out of equilibrium because there is a torque. Okay, so let us see what is happening. Okay, on the system. Okay, these are the details. I'll skip this. Okay, and okay, this is the same slides of before, and where I put the full equations. This is again the spectrum to show that. Okay, what is interesting now? I put an oscillating torque. Okay, so I let my torsion pendulum to do this. Okay, to move like this, to oscillate. So this is a snapshot over the relaxation tau over the relaxation time of the system. Okay, tau n is the period n, so about 2 pi omega d. Okay, and so this is around 5 periods of the driving. Okay. And so what I do, this is the excitation, and I look the response of the system, okay? Now you see, this is just a single trajectory, okay? Corresponding to that. But then what I can do, for example, I can take these windows and then to do synchronous averaging, okay? So taking many of these pictures and then to make the average. And then at the end of the story, I get the mean response of the system, that is this one, okay? And now what I can do, I would like to know the work that this external force is doing into the system. And so, I mean, usually what I do is I multiply the torque times the angular velocity of my pendulum, and then I integrate this on starting at time I, but on a period of time that is a multiple of the driving period. Okay, in sort of to have always the same number of periods that are integrated. Okay, and so you know, you immediately, yes. The thin line is just this is a single trajectory, okay? That is whereas the black line, I take these windows, okay, in different instant, the synchronous starting always synchronous to the driving, okay, and then I averaging. No. This the blue itself. It's the real motion is just the thin line. Okay. Okay. So the point is just exactly what I wanted to say. You make the good point. That is that being delta theta dot a fluctuating quantity. Okay. Of course, I expect that also the Wn or W tau, okay, is a fluctuating quantity. Okay. And so let us see what is happening. Okay. I'll do that based on experimental data. You see that, of course, the more I integrated, the more the distribution shrinks, because if I integrate very long time, of course, I get just the mean values. Okay. But what is interesting here that you see that is exactly what I said. As you see that the peak of the distribution is positive, okay, here. But you see that there are a lot of fluctuations that are negative, okay? That is that because of thermal noise, the response of the mirror or of the oscillators, okay, actually the oscillator does exactly what I was saying before. It actually moves, okay, against the force that is pushing on it, okay? And so this is a typical probability distribution function that you get, okay? And now let me do some thermodynamics of that, okay? So I'll take my equations, you see, and you see that by multiplying this equation by theta dot, we get that the udt, that is the internal energy of the system, so kinetic energy plus potential energy, okay? So the derivative as some time of that is the difference, of course, of the injected power given by mdt over that, minus the dissipated power that is given by, of course, the standard term nu dt theta dot or square minus the work that is done in this case by the thermal bath. Okay. So everything in this is fluctuating. Okay. And so the point now is the following. Suppose that now I integrated this as I was doing. And then you see that I get a very interesting statement, okay, because you see that I have the first principle that I have mentioned before, that is the total internal energy of the system is equal to W tau minus Q tau. But now you see this is not only for mean values, but it's true for fluctuations too, okay? This is an important statement where W. And now you see that I have a way to compute also the heat as measuring W minus delta U. You can measure indeed the amount of heat that is dissipated on the system. And notice that the heat actually contains a part that in principle I cannot measure because it's the work that is performed by the heat bath on the system. And of course, I have in a real experiment, I have no access of this work, but in average I can measure it. Okay. Now let me show another effect. We study now the fluctuation of W tau. You have already seen the fluctuation of W tau, and now we want to know the fluctuation of Q tau, okay, of the heat, okay. And now what you see is the following: that of course, in average, okay, W tau and Q tau have to have the same values, of course, because otherwise I would have a problem as the internal energy doesn't change, okay? But what is interesting that the fluctuations are completely different shape. W is Gaussian and Q has strong exponential tails, okay? And the strong exponential tails actually have a simple explanation because are coming by the fact that you see that this is coming by that W is obtained by a Gaussian variables minus delta U, which is okay, is the other slides, okay, which is the sum of the square of Gaussian variables. So at this point, I expect that the PDF of that should be exponential, okay? And this is actually the case, okay? And now there is the big statement. This is coming from theory, not from the experiment, that is the fluctuation theorem, okay? What the fluctuation theorem says is actually fixing, okay? You see the ratio between the probability of having a positive fluctuations of the system with respect to the probability of having a negative fluctuations. In this case, x of tau can be q, can be w, okay? There are small variations that I will discuss later, okay? But the important statement is the one that the log of the ratio of the probability of that is just a linear function of equals tau times a corrections that goes to 1 for very, very large tau, okay? This is the statement. And then, okay, this is also can be true for, and what is very interesting that the fluctuation theorem actually fixes the symmetry of PDX around 0, okay? Notice that X, okay, important to point out, is not the value minus the mean, is the value of the system, okay? And so indeed, you see this what I plotted, I didn't shift the fluctuation. You see that, so it just really, the system is just fixing the symmetry of the positive and negative values of the PDF, okay? Then, okay, there is another case in which can be studied. You start from equilibrium and then you switch on your torque, okay? In such a case, as you start from equilibrium, everything simplify, and this you show that if tau equals 0, the system is in equilibrium, then sigma tau is true for any tau, okay? This is for what is called the transient fluctuation theory, okay? Now, sometimes people says that, but for a Gaussian it's a triviality. It's not a triviality, okay? And then this in 2 lines calculations, I'll show you that is not. You see that I take this one. Now I assume that my distribution is Gaussian, okay? And now I assume that I also consider that tau is long enough in order that sigma tau is order 1, okay? And now you see that if I do this, this is the variance. You see that is an easy calculation to show that if I apply this theorem to the Gaussians, I get the relationship between the variance and the mean. Okay, and this is quite interesting because it's clearly an extension of the second principle, because the second principle tells you the directions in which the system goes. For example, the heat is flowing from the hot to the cold system. But this theorem is actually fixing the amount of fluctuations we correspond, and these fluctuations are actually related to the mean. But I mean, no problems. You see that the ratio of these fluctuations is actually going down as the ratio, the square root of the mean. So everything is okay, because if I go in microscopic world, these fluctuations become very, very small. This can be undetectable, especially because they are multiplied by 2 kBt. Okay. How much time do I remember? Probably 7 minutes, something like that.
Yeah. I just have a quick comment to add.
Yeah.
So
Yeah.
the last equality.
This one?
Yes, that
Yeah.
also, it's also the curvature of the Kramer function,
Yeah.
from which also you can calculate the temperature.
Yeah,
We use
yeah.
it to calculate the temperature.
Absolutely.
So,
Yeah, absolutely true. Yeah. Okay. Just a short history of fluctuation theorem. The first numerical evidence of fluctuation relation was done many years ago in 1993 by Evans, Cohen, and Morris in numerical simulations of molecular dynamics. And then in 1994, Evans and Searles prove a transient fluctuation theorem, the one that I mentioned before, that is you are just starting from equilibrium and then you switch on your torque. And then there was a proof, more details based also on dynamical system by Gallavotti and Cohen in 1995. And then, okay, there were later proof by Kurshan, Leibovitz, Spohn, Farago, and so on. And then in 2003, there was an interesting comment by Van Zon and Cohen about the fact about the heat fluctuations that actually are not the same, as I said, of the work fluctuations, okay? And then, okay, there is also many other work, many other person has worked on that among Sekimoto, Sasa, Seifert, Gaspar, Gawensky, Esposito, and the other, okay, and I'm on the group. Okay, so this is what is happening. And now let us see whether my PDF, the one that was shown, satisfies the theorem. Of course, I hope that is the case, because otherwise this is a theorem and experimental data, and in this case, are just, I mean, to verify whether the system is actually okay. And this is the case. You see that I plot this in a very strange form. I put this KBT over W tau, the mean, in order to avoid the fact that the mean increasing as a function of tau. And then, okay, I want to see this, okay? And then I want to measure the sigma tau, okay? You see, I start from a probability distributions, and then I construct the symmetry function, this one, okay? By doing the ratio of the positive and negative probability, the probability of the positive and negative events. And now you see that when the slope one is this straight line, and you see that when n is small, okay, that is n is the number of periods in which I have averaged, you see that the deviation of that is large. But as soon as I increase the integration time in which I compute W tau, you see that the system asymptotically goes towards the slope one, okay? So, and now, okay, you can measure this function, and then you can you can measure how the sigma tau goes as a function of the number of integration step. You see that actually is a complicated function because depends on the driving, depends and on tau. And then, okay, this actually can be computed very precisely starting from from the Langevin equations, and then so you see that the data fits quite well the theoretical predictions. Okay. Now, what is happening about Q? You see that Q is just the difference, as I said, of W tau minus the probability minus the internal energy. Okay. Measure on a time tau. Okay, and then you see that this internal energy actually doesn't change as a function of tau. You see this always as two exponentials. And then, okay, by doing this, you can construct the probability distribution of Q, that is just the small q, that is the ratio of Q tau over the mean. Okay, and this is the expression that actually fits quite well for all tau. The PDF, okay? And so now you do again the fluctuations theorem, and then you see that because of the exponential tails, actually in this case there is a saturation, that is this one. This is the asymptotic, but you see that if I limited myself to about to the mean, this is green is the value of the mean, you see that indeed there is the slope one that again appears for a very, very long tau, okay? So the behavior is quite complex of this, and this was pointed out by Van Zon and Cohen, that indeed the fluctuation theorem should be different from for the heat, for the work, okay? So now, what we can do? Yes. No. I cannot start this in 2 minutes. Okay, so let me stop here, and then if you have other questions, let's use the last 2 minutes in order to answer questions or curiosity if you have.
So time for questions.
Can you go back to your PDFs of heat?
Yes, this one?
Yeah. So the regime where you see the agreement with the fluctuation theorem.
The regime, it's more limited, but still you see that it's very big because
Yes.
it's around 1 mean. Yeah.
And if you look at the 1 mean shift in the PDFs,
Yes.
it matches with a Gaussian. It seems to, at least.
Yeah. Somehow, yes, because it's true. But I mean, you will see tomorrow. You can do it in extremely nonlinear case, for example, in the case of stochastic resonance. And in such a case, you see that this is of course accidental because for the central limit, the more you integrate, it doesn't matter what kind of distribution you have, and then at the end of the story, you end up with a Gaussian. But for example, in the case of the stochastic resonance, you will see tomorrow that the distribution is ugly, and but still fluctuation dissipation theorem works. Okay.
Thank you. Questions, folks?
Fluctuation theorem, not fluctuations.
Yeah. So in your power spectrums, where at low frequencies where you have a decay, which you say 1 by f, but I didn't get why that is viscoelastic. So why that is seen as viscoelastic?
Okay, I'll go back on that. So the reason is the following. So let me stick on this spectrum. Where is it? No, it's later. Okay, this one. Okay.
Yes.
The reason is what I said, that indeed this is not that just to the fluid that is surrounding the system. This is actually, if you look at the other spectra that I've shown, this is probably the more relevant. Where did I put it? No. Ah, no, it was before. Okay, let me do. Okay, this one. Okay, this one. Look, you see that if I suppress the fluid and I put the system in air, okay, this 1 over f is still there. The instrumental 1 over f is there, so there is nothing, has nothing to do, okay? And the point is where this is coming from is the fact that any metals have some plasticity. Plasticity means that the system dissipates, okay? So this 1 over f is just induced by the plasticity of the metals in which the system is constructed. And then so I use the same answer that I gave before. That is, I can show you an experiment. You take, for example, an AFM cantilever, okay, and you measure the fluctuation. So a cantilever like this, okay, which is, and then this cantilever can be done, for example, by silica, okay, monocrystals. And then if you do this, you have a spectrum, I've not here, but which is very, very thin if you do this in vacuum, and then it's flat, okay? And then you go into just the instrumental noise because everything. But now if you take the same, you dismount, and then you put, for example, you put a thin layer of gold. You know that the gold is very plastic, okay? So you are increasing a lot of the dissipation, but in a very, very strange way that is on the fact that the Young modulus actually are dissipating and not anymore just a real quantity, okay? So you can simulate this within imaginary part. And this actually, you see that this part is just due to the in my case, to the plasticity of my metals. Again, if I put a layer of gold on a cantilever, that is what I get. And if you want just to make the point clear, you see you can make a scheme like this, because if your C is just, you see, is you say that C at is the standard elasticity, okay, plus an imaginary part that is coming from there, okay, plus the standard viscosity. You see that using again fluctuation dissipation theorem, this is the spectrum that you get. Okay, and now you see that the fact that you have with the 1 over omega is just due to the fact that this omega goes to 0, okay? You see that this disappear, all of this disappear, becomes a constant, and then you expect that indeed, because of this plasticity of the metals, okay, you get this 1 over omega behavior that you observe. Okay? That, of course, is not exactly 1 over omega, because there is a slightly dependence of the C1 as a function of frequency, but is negligible. Okay.
No more questions, then let's thank the speaker for such a nice talk.
Thank you.